Greetings, everybody. My name is Brad Conrad. I'm the director of the Society of Physics Students and Sigma Pi Sigma, the Physics and Astronomy Honor Society. And we are so happy you're joining us here today. We're going to let a couple people pop in the attendee room while I talk at you for a minute. But I just want to thank you for coming to this webinar. We have two guests with us. We have John Mather and Janessa Slone, and we'll go through introductions in a second. But this webinar is designed to get everybody excited about a challenge that we're doing throughout this academic year to help bring great ideas forward and generate new interest and probably new ways of doing things to NASA's attention for the next generation of telescope. And I'm really fortunate to introduce the coordinator for this program, Janessa Slone. She's currently a senior at Embry-Riddle Aeronautical University in Arizona. She's a physics major, former SOC intern and SPS intern. And she's been doing a great job helping out this program. Janessa, do you want to take it away?
Yeah, thank you, Brad. Today I have the honor of introducing one of the NASA scientists behind this challenge, Dr. John Mather. Dr. John Mather is a senior astrophysicist at NASA and a Nobel Prize laureate known for his work on the COBE satellite. He's also the senior project scientist on the James Webb Space Telescope, also known as JWST. So without further ado, Dr. John Mather.
Well, my goodness, thank you, Janessa. I wanted to talk with you today about opportunities for you to participate in designing something that we could possibly use if we can ever find a solution for a very interesting and technically challenging mathematics and mechanical engineering problem. So I want to show you some charts about the Hybrid Observatory for Earth-like exoplanets. So let me see if I can do my thing with the this usual process. Show your PowerPoint slides on the share. So I hope it's working now. Do you see it?
Yes, we do.
Okay. So the Hybrid Observatory, which means we want a telescope on the ground and something in space. So that's what makes it hybrid as compared to an ordinary telescope. And so we have a variety of scientists and engineers leading this. To me, several people here at NASA Goddard in Greenbelt, Maryland. A couple of folks at Jet Propulsion Lab, Jonathan Arenberg at Northrop Grumman, which worked on these Starshade ideas for a long time. John Grunsfeld, an astronaut who went up to service the Hubble Space Telescope and was also Director of Sciences at headquarters, and Brad Conrad, who you already know. So our objective is to find planets around other stars and see if they have life, or signs of life. Now, of course, you can't really tell very well from a distance, but what we want to do is to find chemical signatures in an atmosphere, which could possibly tell us that a place is alive or might be. So the most special and interesting molecule is oxygen. Oxygen is produced here on planet Earth by photosynthesis, plants and algae. And it would disappear quite quickly here if there were no plants and algae. So that's a good, strong sign. We think that liquid water is a prerequisite, so we can search for signs of it in an atmosphere as water vapor. If there's enough water on the surface to have a moist atmosphere, then that's a good hint that that could be a useful place to look. So how would you know? Well, first you have to get an image of a planetary system and then get spectra. A spectrum spreads out the starlight and the planet light into colors, so you can see the particular signs of chemistry. So I'm not going to go into that in any great depth, but I'll show you a synthetic spectrum to see what we would see if we could do this. So where would you look? The best place to look, if you could, would be stars like the sun, because there is one known example, obviously, where there's life in the universe. It's here. And so this is a good place to look if you can do it. However, it's an extremely, extremely difficult observational challenge because we are looking at a tiny planet. The sun is 10 billion times as bright as planet Earth. So this is just an extremely difficult optics problem. The planet is quite close to the star. And no matter how big your telescope is, it still looks very close to the star. There's an awful lot of glare. So what is the NASA plan? We have a recommendation from the National Academy of Sciences committee. They do this every 10 years, and they write us what they call a decadal survey. and they asked for something we're now calling the Habitable Worlds Observatory, about 6 meters in diameter, in a telescope in space. That's the same size as the Webb telescope, about, and it needs to have more perfect optics and an instrument called a coronagraph. A coronagraph blocks the starlight and lets us see a little tiny planet next to it, but it has to have about 100,000 times better performance than the Webb telescope. So the cost and the launch date are just kind of guesses at the moment. They're what we're wishing for, but it's not impossible. So I want to see that done. I want to see it while I'm still alive. So what alternatives are there? Well, aside from building space telescopes, there is one idea that's circulating, which has been actually pretty old by now, but I've been pushing on it. And so it's gotten interesting because we are now building gigantic telescopes on the ground, which would make this worth thinking about. If you could use the telescope on the ground and put a star shade in space in just the right place, so it would cast a shadow of a star onto the telescope on the ground, you could possibly do this project that way. So calculation says such a device could observe about 1,000 times faster, or maybe more, compared with the baseline plan of the 6-meter diameter space telescope. And it would have also about 6 times better angular resolution. So this would be enchanting if we could accomplish it. So is this hard? Well, yes. I want to show you why. So here's the sketch. We need the star shade to be about 100 meters across, because we have to cast a shadow over the distance of about 170,000 kilometers. And why do we need that distance? Well, number one, we need the motion of the star shade to be matching the motion of the observatory as the Earth spins it around. So that tells you the velocity, and you have to have at least this altitude, or else the star shade will hit the Earth when it comes back into the perigee. Okay, so that tells you what orbit you need. Then we say, well, in that case, we know about what orbit we need. We also need to have a rocket thrust during the observation, because we'd like to keep the alignment, keep it all set up during the exposure time. So 1 minute might be a long enough exposure for some purposes, but if you want to get a spectrum, it's going to take you more like an hour. So that means you have to match the acceleration of the observatory as well. And it accelerates because, of course, as the observatory spins around the Earth, on the surface of the Earth, it's being accelerated by that rotation. So this is pretty tricky. So what else are you going to need? We're going to have a little laser beacon in the center of the star shade pointing down at the telescope on the ground. Now, if you could do this, we could get a nice crisp image, as the synthetic image on the right hand shows you. Earth, Mars, Venus, and Mars would jump right out in an exposure time of 1 minute, which is super spectacular. No other observatory concept can do that. So worth trying. So I told you briefly about spectroscopy, spreading out the light of the potential Earth out into its colors and see, does it have the signature of particular molecules we're interested in? So the answer is yes. So on the vertical axis, we have the number of electrons per second coming in from a hypothetical planet. On the horizontal axis, we have the wavelength in nanometers. So this covers roughly the visible wavelengths that you and I could see, and a little bit of near infrared. So the things to look at are right here. This blue curve is a synthetic Earth. So we're seeing little notches in the curve owing to oxygen and water, and oxygen and water, and more water and more water. That means this number of electrons per second isn't high, but it's more than a tenth of an electron per second. So that means if you've got an hour or a minute, you can get a useful number of electrons or detected photons. So that's enough to be able to say, yeah, I saw signs of life. Oxygen would be visible. And that's interesting because it's true even through the atmosphere of the Earth, which has its own oxygen and water and partially blocks the starlight and this Earth light that we're trying to receive from way out there. Farther up on the chart, there are curves for synthetic versions of Jupiter or Neptune if they were brought in closer to their star, and so those signals are much greater, and we can observe them with more spectral resolution as well. So we would be able to see interesting compounds like methane in such a hypothetical planet. So it's worth trying. So I told you we were building great telescopes on the ground, and they are in various degrees of completion. The one on the right-hand side in the top corner is quite far along. I show you a picture of just flattening the top of the mountain, but they've actually already started building the bottom structure of the telescope, and they are manufacturing some of the roughly 1,000 little hexagons that it takes to manufacture this telescope. You can see what a massive structure this is, because you see the little cars here in front of the building. And so the general idea is a 39-meter telescope is totally immense. The US-led partnerships over here on the left-hand side are a little smaller, and this one would have 7 circular mirrors. This one in the bottom would have another roughly 1,000 hexagon mirrors. And so far, neither of these projects is fully funded, so we don't know quite how long they're going to take. But this European one is scheduled for first light in a couple of years, and we'll start to be able to say, yes, it works the way we were hoping for. So now, however, I want to introduce a subject called adaptive optics. When you look through the atmosphere of the Earth, you can't get a very crisp view of distant stars because the atmosphere of Earth is turbulent. So it means that a telescope you can buy over at Costco or someplace like that gives you just about as sharp an image as the biggest ones can get you, unless you do something about it. So what do? We receive the light from the telescope. We make it bounce off an adaptive mirror, a little deformable mirror, and we see if we can correct the distortion of the wavefront due to the turbulence, and then control it so that we get a nice sharp picture. So you can do this if there's something to focus on. So if you have a bright star out there, you can do this. If you have a laser shining down from the middle of the starshade, you can do this. So that is basically solved problem in principle. And so people are already doing this quite a lot. The right-hand side points out that you may already have encountered this kind of system if you go to the eye doctor. They need to see through your eyeball, through the lens in your eye, to see how are you doing with your retina. And so they can use very similar ideas to compensate and get a nice sharp picture. And if you're very interested in perfect vision, they can use this information to correct your vision so it's much better than it would have been. So practical applications of astronomy. So let me talk about what wavelength to use. The atmosphere of the Earth is pretty bright at infrared wavelengths. And so here is a picture showing how bright is the sky in astronomers' units of Janskys per square arc second. So this is a plot of the brightness versus wavelength. So the green area is more or less the wavelengths that your eyes and mine can pick up. Visible light and near infrared is added on. And so the sky is really pretty dark compared to what it would be in outer space, which we have labeled here as a L2, which is where the Webb telescope is. So the sky on the ground is 5 or 10 times brighter than it would be in outer space, but that's not insurmountable if the telescope is big enough. Then over at longer wavelengths, you see, well, it actually gets a whole lot brighter. And this is because there are chemicals in the upper atmosphere of the Earth, and they are glowing. And we can't avoid that. So anyway, this tells us the visible wavelength band is the place to go if you can possibly do it. So the upshot is, if you can make this telescope on the ground work with adaptive optics, it can be much, much, much more sensitive than a telescope in space, especially if the one in space is smaller. So worth trying. That's what gives us an idea of the orbiting starshade a special advantage. So what's the problem? Well, first problem to solve was what orbit? So I think I told you briefly about that. And it's a long elliptical orbit. We call it astrostationary because the idea is the Starshade will appear to hover in front of the target star for a little while. And I mentioned already that we need rocket thrust to match the acceleration of the observatory. But now we have another problem because rocket jets are probably bright. So we don't want rocket jets to be preventing us from seeing little Earths way out there. So the idea here is we'll turn them on and off. Turn them on for 10% of the time and turn them off for 90% of the time. So then you just close your eyes when the rocket engines are on. So this tells us how much acceleration we have to subject our Starshade to, and then we have to recover the right shape after the pulse. Well, okay, so that is a solved problem in principle, and then we also have to do something else to change the orbit every time we want another target to go to a new star. This is also expensive. So rocketry is expensive, and the amount of effort you have to put in is proportional to the mass of the thing you're moving. So the answer is build a very lightweight Starshade. This is why we're asking you to help. So what shape do we need for the Starshade? Here's a sketch of one. What we have in the idea here is we have a big circle in the middle, which is opaque. Then we have pointed petals around, and the sketch is showing you the mechanical structure to hold them up, but those petals are also to be opaque. So they cast a shadow on the telescope, and the exact shape of those little petals is specially designed to suppress the amount of diffracted light that would fall on the telescope. So diffraction happens because light's a wave, and it bends around corners, and we want it to not bend in the direction of the telescope. So imagine the telescope mirror is in the middle of the shadow of this big thing, and the light bending around the petals does not go towards the telescope. So what's the challenge we're asking you to deal with? Number one, make this very large. It has to have the right shape, more or less. It has to be about 1,000 kilos. That's our objective, because if we could get that light, then we could solve a lot of other problems too. It has to be quite stiff, because after we've finished pushing on it with a rocket, we have to be observing with it. We have to understand how to unfold it after launch, or whatever other way we do. And I'll show you some ideas that people have already tried, and they're not good enough quite yet. But the point I want you to think about is usually when people say, I'll make you something stronger, they'll say, I'll make it heavier. But that doesn't help you very much, and the thing that you're trying to make stronger weighs more when you make it stronger. So that's why we're asking you. So here's our story. We defined our requirements. We know how much to do this. We discovered that NASA has a challenge office, and they were able to set us up with a community challenge on grabcad.com. It's a community, online community of many, many thousands of users. And you can say, here's my challenge. We can even offer prizes for solving those challenges. And I'll show you a couple of the things that they did. So then the second step is to ask for you all to help us with the designs and see if we can do better. I'll show you what they got from the grabcad.com challenge. But before that, I want to show you a couple of things that the JPL did. JPL got quite far with designing something to use with smaller telescopes in space. And so here is one that they actually designed, and you'll see it unfold. Of course, you can find these things online yourself if you do a Google search for Starshade deployment. But here you see how they've got this working out in a laboratory. And it's very cool. They've got things that deploy using stored elastic energy. That is to say, they bent them to fit. And here's the model doing this. It's actually easier to draw it than it is to build a real one, but you see a very complicated thing unfolding there to become basically a bicycle wheel held together with spokes, but the bicycle wheel rim was folded up during the previous stage, and here it is all unfolded. It's a magnificent example of engineering, but I'll show you how it would apply to us if we could do something like that. Before I do that, I want to show you their version of deploying one of these things in outer space. So let me see if this will play properly. Here we go. Here's their concept for the Starshade rendezvous mission, with a telescope and a Starshade being launched at the same time. So there it is, very rapidly unfolding in space and becoming the Starshade that would then be used to block the light of a star and let us see the little planets. So that's what we would like to do too, except our idea is to have the telescope on the ground and the Starshade in space. So this is what it looked like when we tried with JPL teams to squeeze an even bigger one into the rocket. And you can see it's an extremely snug fit inside the top of the rocket. It's a Falcon Heavy rocket. And even after we did that, it wasn't quite good enough. We couldn't get enough fuel into it, and we couldn't even quite fit the size we wanted. So it's not logically impossible. Of course, there are bigger rockets coming, but this was expensive. For a general rule of thumb, price and mass are roughly proportional for similar kinds of technologies. So twice as much mass, twice as much money. So let's see if we can find a lighter weight version. So this is one example of how to go. The SpaceX folks are building up a Starship, which would be a cheaper launch vehicle and enable us to use different shape of payload fairing. So if that changes the options for us as to how to get something up there and into the right orbit, then that's interesting for us. Right now, we're kind of hoping we can find a way that doesn't require such a large spaceship, because that gives us more choices. So what do we have to accomplish? Well, we tell you roughly this shape that we have to accomplish, a big pointed sunflower. We have to have the ability to have the sun shining in from the side almost, pretty close to the plane of the shade. That's so we have enough choices about where to look in the sky. There have to be at least 2 layers of the opaque membrane, because otherwise starlight and sunlight could get through. It has to have sharp edges because the sun is shining on the edges, and we don't want them to be luminous and simulating a star or a planet. And we need the whole thing to be able to withstand some acceleration. Just a sec. We need the whole thing to be able to withstand acceleration and then recover the right shape. And we reserved an empty cylinder in the center for a place to keep all that rocket engines and things and fuel tanks. So if you want to go look at the grabcad.com, you can see all of the things that people did. You just, I think you have to set up on your own account so you can see it. But then when you get there, you can look for the challenges that have been shown in the past. There are about 50 contributions that came into us, and none of them actually come close to meeting the mechanical requirements. So I'll show you a couple of examples because it shows creativity. Here's one. It's the first place that we chose. You can see it's a lot of what we call tensegrity, which is a combination of cables under tension and straight, stiff objects in compression. A concept that was pushed a lot by Buckminster Fuller quite a few years ago. So that's one. It's quite different, and I don't know if it could be made to work, but it's an interesting concept. Here's another one where they decided, oh, let's make the pedals not be flat, and make them stiffer by making them in 3-dimensional structures instead of 2 dimensions. So this is otherwise pretty similar to the JPL designs that I showed you. So if you want to get inspiration, you can go there, but we're actually hoping that you will have your own inspirations as well. So, well, generally we've been looking at bicycle wheels folded like the one that I showed you. There's a possibility of an umbrella, although so far I haven't seen a good one. You could imagine making a truss, something like you would build like a bridge or like the Eiffel Tower. And maybe you'd put it together in space, although rather we didn't have to. Or you could make something that inflates, and you would rigidize it after launch. Of course, a balloon that you put up would eventually leak. So that's because there are little tiny dust grains in space that will make holes in your balloon. So you can't do that one, but you could make something that gets stiff by chemical reactions, say your epoxy cures or something like that when you get there. So that's one thing to push on. There are quite a few different materials you can think about. You can buy a deployable truss. It's called an astromast. That's a trademark. You can buy them, and they're very well engineered. You can make a hierarchical material. That is to say, a big truss made out of little trusses. And the Eiffel Tower is such a thing. It's actually third order, which means that the tower is a truss. The elements of the truss are trusses, and the elements of the trusses are themselves even smaller trusses. So I think everybody knows that carbon fiber is a really wonderful aerospace material. It is really probably the best in terms of stiffness and strength to weight ratio, but it's a little tricky to work with. There are things called bi-stems, which are flattened out structures like carpenter's rulers, where you get, say, a pair of them. They want to be straight, but you flatten them out, and so they aren't straight. So many possibilities for you all to think about. I'm very interested in what you're going to tell us about how a model will represent something that we don't know and that we're going to learn from. So if you make a model out of the same materials that you would use for something that's 100 times bigger, it's going to be very different in behavior. So we'd like the behavior of this model that we ask you to do to be similar enough so that we can learn something from it. And in particular, we'd like it to have strength and stiffness related to the real one so that we can tell what the real one would do. So it means, in particular, build your model out of weak and soft materials so that they would fail in similar ways to what the big, expensive one would do. So I'm not going to tell you how to do this, but it's a really interesting and important part of the challenge we're asking you to take on. So let me wrap up here, and let's see if we can have questions from our teams, because there's an awful lot to think about.
Thank you, John. That was awesome. So we're gonna give some people to ask some questions in the audience. Janessa, would you like to start us off with a question?
Yeah, of course. I do have a question for you, Dr. John Mather. How can the collective ideas from undergraduates specifically help advance future telescopes like the Nancy Grace Roman Space Telescope?
Oh, okay. Well, I would say all of the telescopes we're thinking of putting in space could use a Starshade. So we have not agreed to do it yet because, for instance, the Starshades that we can draw are big and heavy. And so we also are not 100% sure that we need them yet. But by the time we decide we need them, I'd like to be able to say we can build them. So that's why the challenge to you, the students, is so important for the possibilities of future astronomy.
Great, thank you. And we do have a question in the question box. For the Starshade idea, does the atmosphere blur the image for the ground telescope, or is that not an issue?
Yes, the atmosphere would blur the image, but we want to do the adaptive optics. So that means we should be able to compensate for the blurriness caused by the atmosphere well enough. So a laser beacon right in the middle of the Starshade is plenty bright. And so we know basically what to do. And people are already working on that part of the problem.
So, John, I wanted to ask a quick question, if I may. I think this would be an excellent project for students to work on over the course of the semester. Would you have any advice for student groups that would be looking to do this, or faculty that might be looking to implement this in their classroom for the semester?
Well, yeah, it seems to me that developing ultralight objects and that go into space, that hold themselves up into the right shape, is a really interesting and difficult challenge. In many, many schools, people used to build balsa wood bridges to prove that they understood engineering. And the idea was you should be able to hold up yourself and your professor at the same time on your little balsa wood bridge. And this is an altogether different challenge, because we have to think differently when the thing you're holding up is only the structure you're building. And so this will enable us to extend our thinking out to giant space structures of all sorts. People want to build solar arrays in space. They want to build spinning spaceships out there so that we can have artificial gravity. There's a whole lot of things where the structure that you're building is the main problem. So the ultralight structure that is as stiff and strong and cheap as possible, that's a great challenge for all of us to think about.
Awesome. And for those that might be interested in doing this semester or this spring, I'll put in the link, or in the chat, a link to the challenge. If you're interested in learning more about the challenge, or if you're interested in participating, I would encourage you to go to the website. It's a very detailed set of things we're asking, and we give a bunch of hints and tricks for people that might be interested in starting. At the bottom of the page, there's a bunch of resources. You can see some of the work that's previously been done. And you can also reach out to Janessa, who is the one helping to facilitate this challenge. Janessa, could you put your email address in the chat for everybody?
Of course I can. I might not have access to send it to everyone, but I will put it in.
I got it right here. I'll go ahead and drop it in for us.
Yeah.
Okay. There we go. And John, just one final question I had. So let's say somebody comes up with a awesome idea and it makes its way to you. Is there a chance that this could be implemented in future NASA projects?
Well, I would certainly hope so. Right now, we don't have a plan to build a Starshade because it looks too difficult. And it's not so urgent yet because we haven't done the easier parts first. But I think there is really a chance. When I showed you that this observatory combination could be at least 1,000 times faster than the telescope we are planning to build, that's a big enough advantage to be worth trying for. So at the moment, people can't say yes because they can't see that it's possible. But if they did see that it was possible, then maybe it could happen. So I'm in the, if it's not impossible, let's try it business.
I like that motto. And I think we have two other quick questions. Can the Starshade project be used to detect other astronomical objects other than exoplanets? I mean, more objects which can lead to give more information about outer space.
Yeah, there's one other kind of thing that we're really interested in that's hard to study, and that's called a active galactic nucleus, also called a black hole. The center of every galaxy seems to have a black hole in the middle, and sometimes a million, sometimes a billion times the mass of the sun. So we are trying desperately to figure out how they got there. How do they grow so big? And so the critical question is, what's next to them? What is orbiting around them? How is material able to fall in? So it's a hard thing to do because the darn things are so bright that they're casting anyway, there's the glare problem again. So if we could overcome the glare problem and see all the way into the neighborhood right around the black hole, that would be very, very helpful to a whole other branch of astronomy. I wanted to add one other thing too, which is that we could also try flying the laser beacon without a Starshade, so that we would be able to enable a high performance adaptive optics anywhere in the sky. And it's a precursor mission that we really ought to try, in my opinion. So we are talking with the people building big telescopes, and we're talking with team members at the Keck Observatory in Hawaii, and they're all quite interested. So we'll see whether this is something we could do as a precursor.
We do have another question in the box. It says, hello, I am the lead design engineer for a university team that is designing a small scale deployable Starshade for a 1U CubeSat that will fly in LEO. Do you have any tips for designing and fabricating such a small structure?
Well, I think for a small one, you have a lot more choices than you do with a big one. So you don't have to make it ultralight. If you were to scale a 100 meters device down by a factor of 100, its mass would scale by a factor of 10,000 or more. So you'd end up with something that was only grams instead of kilograms. So you don't need to solve that problem for a if that's your CubeSat mission. But it's worth trying, because demonstrating a CubeSat version would illustrate to people the power of the concept, and say holding the positions and doing science with it isn't as hard as people think. So good luck on it.
Okay, and then we have one last question. But can black hole study be more difficult, as we cannot shade any kind of star near the black hole? So I guess the question is, how can a star shade be used to study black holes more efficiently?
Okay, so you can use the star shade to block out the black hole's light itself, so you can see the neighborhood around it to see what's falling in. So this is a hard problem, and we are not yet. We don't know that we have to do this. We haven't tried the easier version yet. So the first thing to try when we get our new big telescopes is to get the adaptive optics working as well as we can without a star shade, and then see, do we need a star shade? So first things first.
Well, John, thank you for answering all the questions and the fantastic presentation. We'll hopefully be having John back later on in the semester to help give us a little bit more input on some of the different techniques and processes around this project. For those that are joining today, thank you for attending. And from all of us at SPS, thank you.
And thank you all for coming. I look forward to seeing what you send us.
Okay, have a great rest of the day, everybody.
Thank you.